x1 bar, x2 bar, cosine, and omega 2 So you have two eigenfrequencies. Second step, figure out what is the eigenmode. Eigenmodes basically corresponding to each eigenfrequency, you need to figure out what is the eigenvector of that A matrix. So when omega equals to omega 1, just substitute omega 1 into A matrix, you will have minus omega 1 squared, m0, 0, 2m, plus 2k, minus k, minus k, k. x1 bar, x2 bar. This is a eigenvector or eigenmodes corresponding to the second eigenfrequency. And next step, assembly all of the eigenmodes into a matrix. You will get this phi matrix because we're going to use this phi matrix to do the coordinate transformation. So you just assembly them one column by one column, phi 1, phi 2. If you have more than two eigenmodes, you just put them more put more columns into this matrix, phi 1 until phi n. You only have two columns because you only have two eigenmodes. So the first one will be this one, phi 1. Second one will be this one. This is phi matrix. After you form the phi matrix, you can diagonalize the mass matrix and K matrix. When you look at the mass matrix and the K matrix for this system, this is a mass matrix, this is a K matrix. Actually, the mass matrix is already diagonalized. K matrix is not. So we can still perform the diagonalization, use the notation. For spring mass matrix is already diagonalized because it's discretized already. But for elastic bar or beam, it's not going to be diagonalized. You need to use this notation. So phi t m phi. This is the general notation for you to use how to do the diagonalization of mass matrix. Phi is this one. So phi t means phi transpose. Phi transpose means 0.56, 1, 1, 28. Because phi is symmetry. When you look at that phi matrix, is symmetry. Phi transpose basically is equal to phi. And M matrix, M0, 0 to M. Phi matrix, copy that phi matrix. Three 2x2 matrix, put them together. You will get another 2x2 matrix, but it's going to be diagonalized. Actually, it is diagonalized already. So, but it's going to be normalized. Not only diagonalized, but also normalized. This is the result. You have 3x3. You have three 2x2 matrix. Put them together, you get another 2x2 matrix. M, I take M out of the matrix. So this is a diagonalization of mass matrix, and we can do the same thing for K matrix. T, K, phi. Phi is the same. K is the stiffness matrix. So it's this one. This is a stiffness matrix. Original stiffness matrix. 2K, minus K, minus K, K. And times phi. another 3 2x2 matrix. Put them together, you can get a diagonalized K. From these two results, you can figure out why this phi matrix is so useful. Because when you put this phi, do the operation like this, you diagonalize this K. You diagonalize this K. Otherwise, this K, you have non-zero at long diagonal term. It's not easy to solve. But after you do the operation using the phi matrix, everything becomes zero on that non-diagonal term. Okay, you only have diagonal term along this on Q11 and Q22 value. You only have value for Q11 and Q22. You do not have Q12 and Q21. Why it is useful? Before we go to the equation motion, we also need to do the force transformation from coordinate to the normal coordinate. Basically, this procedure is do the transformation from normal coordinate to the from Cartesian coordinate to the normal coordinate. This is external force applied on M1 and M2 in Cartesian coordinate because you multiply phi t on both sides of the equation. So you need to do the same equation for F. Okay? So F1t, F2t. And then you will get one column. Maybe we should put T here. T, T, T. 2x2 matrix times 2x1 column. You get 2x1 column. So you convert everything. Convert M, K, and F from Cartesian coordinate to the quantity in normal coordinate. And then we write the equation motion. We can write the equation motion in normal coordinate. So basically, it's MD Q double dot plus KD Q equal to FB. This is the general form for the equation of motion in the normal coordinate. We derived this, right? X equal to phi times Q, and then we diagonalize M and K, we get this. So this is the equation of motion in normal coordinate. If we use MD, KD, and FD, what do we have? We just copy MD This is MD. We obtain Q in normal coordinate. We will have Q1, Q2. Two masses, 2 degree freedom. KD, we just copy KD. KD is here. Q1, Q2. This is KDQ. And equal to FD, you already convert FD becomes F1T plus F2T. F1T minus this is the two equations of motion in Q coordinate. When you expand this matrix form into two equations, you will see each equation only contain one unknown. Let's expand it. So the first one is this row times this column. The second one is this row times this column, right? And this is given F1 and F2 is given, loading. So the first one will become M Q1 double dot, because you have a 0 there, non-diagonal term is 0, so Q2 double dot will be gone. And second one, K Q1 equal to this equation is in terms of Q1 only. F1, F2 is given. So in principle, it's much easier to solve for this equation than the previous equation motion. The original equation motion, the first equation is x1, x2 couple. It's not easy to solve, but in this one, you have a general solution for this kind of equation. And if you explain the second one, this row times this column, this row times this column, you can get another equation motion. So this is the first equation motion, this is the second equation motion in normal coordinate. Basically, in principle, we can solve for this. But when you are trying to solve this, you are going to need the initial condition. The initial condition is given in terms of x, not q. So that means we not only need to convert the equation motion from x coordinate to q coordinate, we also need to convert those initial conditions. This is the initial condition, 4 initial conditions. We also need to convert those initial conditions from Cartesian coordinate to q coordinate. So before we solve these two equations, we convert those initial conditions first. Follow the same phi matrix. If this is the initial condition for Q1 and Q2, initial displacement in normal coordinate, phi t x10, x20. This is how we use the phi matrix. Use phi matrix to perform the coordinate transformation everywhere. No matter its force, velocity, displacement, boundary condition, initial condition, not boundary condition, initial condition. Okay. Use phi to transform this initial displacement. You will get initial displacement in q coordinate. So because phi is already solved, you will get this one is 10 plus x20 . So this is the initial condition in q coordinate, initial displacement basically. And you also have initial velocity. As I said, you can use the same phi matrix to perform the transformation. x10 dot, x20 dot. These two equations give you the initial conditions in q coordinate. So basically, this third equation, fourth equation. When you look at the two equations, equation 1 and equation 2 are the equation motion in terms Q1 and Q2. If you solve equation 1, you can get Q, but Q will be in terms some material, will be in terms of some constants. Those constants needs to be determined by initial conditions. This is the initial condition you can use for Q. So everything is in terms of Q now. Equation motion, initial condition, and you can solve for Q. We're not going to solve for Q in the exam with no homework anymore, right? So I'm going to stop here because anyway, you will not have time to finish solving for Q if I give you problems in exam like this. But the procedure is like this. After you have these 4 equations, basically, in principle, you can solve for Q. But what you need is X, right? X equal to y q. This is how ANSYS perform the model analysis. ANSYS basically solve for q first.